Good morning, everyone. My name is Matt Roberts. I'm a postdoc here at CBE in charge of the Lifecycle Assessment Research Area. Today, I have the exciting honor to present the California Carbon Report that I've been working on in collaboration with the team at the Carbon Leadership Forum, also referred to as CLF, hosted out of the University of Washington. Just to give you a bit of more background, the report, we're analyzing the embodied and operational carbon impacts of 30 buildings, new construction buildings across the state of California. We're using information and data that has been collected from industry practitioners. And the idea is that we are wanting to investigate both current reporting practices as well as trying to identify ways of improving the completeness and comparability of standard reporting and carbon assessments across the whole lifespan of buildings. So this report, it will be hot off the press. We are going through the final copy edits and layout formatting of the final report. So we'll be doing a news distribution of it, hopefully within the next 2 weeks. And it's important to note that the funding for this work was done through a variety of foundations. And we like to especially thank ClimateWorks Foundation for being the funder for our proportion here at CBE. So just to give you guys a bit more of an idea about the data collection process. So like I said, this is using industry practitioner data. So the firms that we collected information from were a variety of engineering and architecture firms. They had to follow standard reporting templates and modeling parameters for what was modeled and how it was modeled, and then the outcomes of it. So then this data was collected along with the building attributes and characteristics by CLF, and then we did some data alignment and processing to make sure that there wasn't any outliers in the data set. And then finally, we arrived at the data set of 30 new construction buildings across the state of California. To give you guys a bit more of a understanding of the type of buildings that we're working with. It's a variety of use types, including quite a few commercial office buildings, some multifamily, and then some buildings that are classified as other, both in terms of just other and then commercial other, including some healthcare facilities, lab facilities, and a few warehouses. The buildings had a variety of primary structural systems, from purely concrete structures to concrete and steel and timber frame, and they had a variety of sizes as well. 21 of the buildings were 5 stories or less, and 12 of the buildings were below 50,000 square foot. So the data set is skewed towards more smaller building sizes rather than larger buildings. And it's just wanted to give you guys a bit of a geographic understanding of the buildings. They're centered around the main population centers in California, where new construction is predominantly being located currently. So these are the life cycle stages of a building. Hopefully, we're all getting familiar with these with all the presentations I've been doing. So this is the life cycle stages that are used to categorize the environmental impacts that happen at different stages of a building's lifespan. In orange, we have the areas of scope from the temporal aspects that are included within this study, including the product stage, which is A1 to A3, transportation, refurbishment and replacement, and then some stages in end of life as well. And then from the operational perspective, we have modeled the operational energy use of the buildings using average annual building demand data and average annual grid carbon intensity. So the system boundary for all life cycle assessments is one of the most crucial aspects of the study. So I'm going to take a moment on this slide just to walk you guys through it. The system boundary basically establishes what's included in the study and what's outside of the study, and helps to allow buildings to be compared against one another and give context about what is going on in the assessment and how the assessment was done to begin with. So from the embodied side, we have the structure, enclosure, and interiors. Important to note, the first set of results I'm going to show you is only for structures and enclosure, because 19 of the 30 buildings included interiors, and we're going to be looking at the implications of expanding the scope to include interiors later on in the presentation. From an operational perspective, we have assessed both the electricity use and the natural gas consumption of these buildings, again, based off of average annual values. Outside of the scope, This includes, from a physical aspect, we have the MEP systems, site work and landscaping, and FF&E. Furniture, fixtures, and equipment is typically not considered within a lot of life cycle assessments for building scale assessments. However, especially for commercial offices where there's a high turnover of tenants, there's a lot of replacement and exchanges of the fittings and equipment in those spaces. So that equipment typically doesn't reach the end of its life. So it's a lot of wasted resource there, and the impacts of those building elements add up cumulatively across the full lifespan of the building. And then other considerations that were not included in the study are refrigerant leakage, time of use, operational impacts, the influence of biogenic carbon, which can have a significant impact and influence on the results of timber construction, as well as other environmental impacts. So this study is purely looking at global warming potential assessed over a 100-year time horizon, and it's looking at what we typically refer to as carbon. So what are the embodied and operational carbon impacts of these 30 buildings? The data set is quite varied. There's a lot of variety going on in this data set. Again, in orange, we have the embodied carbon intensity. The values reported here are normalized by building area to allow for the buildings of different sizes to be compared to one another, and they're reported in kilograms of carbon dioxide equivalents per meter squared. So the buildings have been categorized based off of the generic building typologies that we've assigned for this study, and then each bar is assigned with one building. So in orange, we have the embodied carbon intensity of the structure and enclosure. Dark blue is the operational carbon intensity from the electricity use, and then light blue is the operational carbon intensity from natural gas consumption. Few outliers in this study. On the right-hand side of the graph, there are 3 buildings that are basically ultra-low warehouse storage facilities, which is why you see barely any operational impact for those buildings. And then the large commercial non-office is a lab facility with very high energy loads that were not able to be electrified compared to other buildings that can undergo further electrification. Looking more specifically at the embodied carbon impacts by building element, this is again structure and enclosure, and then some elements that are not classified by building typology. And this is reported by the CSI building typology. Overall, the structure is typically larger than the enclosure. This is pretty standard that we're seeing across many other life cycle assessment studies and whole life carbon assessment studies of buildings, which is great. It's a nice sense check to show that like the results that we're getting from industry practitioners across California is aligned with what we're seeing throughout Europe and elsewhere in the world. The box plot on the right is just showing you again the range of operational carbon intensity compared to the embodied carbon intensity of the buildings. The embodied carbon intensity ranged from about 190 to 690 kilograms of CO2 equivalent per meter squared. A1 to A3 for the structure and enclosure was the largest. This is associated with the product stage or upfront embodied carbon impacts. So this is the impact of producing the materials before it then gets shipped to site and then installed during the construction stage of the building. And then again, the structure ranged from about 130 to 560 kilograms of CO2 equivalent, with the enclosures ranging from about 20 to 250 kilograms of CO2 equivalent. So again, these values are only looking at the embodied impacts of structure and enclosure. So what about interiors? So we had 19 buildings that reported the embodied impacts of interiors to some degree of completeness. So here we have split out the embodied impacts of interiors from the embodied impacts of structure and enclosures. So the first box plot is showing the embodied carbon intensity of these 19 buildings, just looking at the structure and enclosure of those buildings. Whereas when we add in interiors, we're seeing an overall shift, an increase of the embodied carbon intensity of these buildings by 65 kilograms of CO2 equivalent per meter squared on average, which equates to about an 18% increase in embodied carbon intensity when compared to the embodied carbon intensity of the structure and enclosure alone. So looking at the buildings overall from a material contribution analysis, the material breakdown really depended on the structural type or structural system that was used in these buildings. Overall, concrete was the largest contributing factor, typically associated with the structural system of the buildings, ranging from 70 to 490 kilograms of CO2 equivalent. And then metals was typically the second largest material contributor to embodied carbon intensity. So what's important to note is that building scale life cycle assessment is a puzzle, and we still really don't know the full picture of what's going on. So this study is a great place for showing and describing where we're at in industry, but it's also really good at highlighting what we need to do to get to the point where we can say, this is the environmental impact of a full building across its full lifespan. So what we've done is we've categorized the next steps in future work and areas that we need to address in life cycle assessment for the building industry into three main categories: methodological considerations, physical scope, which is the building elements, and then temporal scope, which is the different stages of the building's lifespan. So in terms of methodology, we need to do a lot more research into how biogenic carbon content is calculated, quantified, and reported in building scale LCAs. We need to incorporate time of use factors into our modeling assessments and reporting practices, and also look at both short-term and long-term climate impacts of the design decisions that we're using in the building industry. Certain ideas and practices are having a longer-term impact over time, whereas other strategies are having a more immediate short-term impact right now. In terms of physical scope, renewables and energy storage are a hot topic that are being incorporated into a lot of building elements. However, it would be ill-advised to assess and report the benefits of using these systems from an operational perspective without also quantifying and accounting for the embodied impacts of these systems. We're seeing in certain cases, the embodied impacts outweigh the benefits from the operational perspective. We need to expand the scope of the studies to include the MEP systems. These systems typically use a lot of metals, which is high energy, and require a lot of processing impacts to produce them, and are combined of a variety of very different components. And then interiors and FF&E, again, going back to the interior slide, we saw that just based off of how these were modeled, we saw an 18% increase compared to structures and enclosure. So the more building elements that we have in these studies, the larger the impact is. However, that isn't necessarily the scary thing. What is scary and more critical is the fact that the more elements that we look at, there's more potential and more areas to find greater impact reduction across the full building element category and the full building lifespan. And then site work and landscaping. A lot of the time in urban areas, this isn't too much of an issue because the building typically consumes a lot of the site. However, in other areas and more infrastructure projects, the site work and landscaping, which includes grading, excavation, and groundwork, that can be quite impactful and intensive. In terms of temporal scope, we heard from Paul earlier today that refrigerant leakage can be quite impactful. So we're doing some work behind the scenes to hopefully incorporate that into some of these building scale assessments. Maintenance, repair, and refurbishment, which is life cycle stages B2, B3, and B5. They're often typically considered to certain degrees, and very broad brushstroked assumptions are being used. So we need to improve how those are considered, as well as construction and deconstruction, as well as module D, which is both the impacts and perceived benefits from exporting energy from a building to a grid network, as well as any perceived benefits from reusing materials and recycling materials. So this is one area of work alongside all these other areas of work that I've been working on for the past 6 months, including some proposals that we're still waiting to hear back on. I'm going to be running a breakout session today on improving the completeness and comparability of LCA studies in buildings. However, please feel free to talk to me about any and all things life cycle assessments in buildings. So thank you. And just as again, a quick reminder that we will be sending the report out once it is finalized and published. So thank you.